Welcome everybody, so thanks for coming to my talk. I am Enzo Krans and I will talk about Trakt, a generic preprocessing tactic for theories-based proof automation. This is joint work with Denis Cousineau and Assia Maboubi. So first I will talk about proof automation in Coq because that's the context of my work. So if you take the set of formulas you might want to prove interactively, if you take a subset of this, let's say it's a theory T, which is decidable. It means there exists a DT, a decision procedure, for which any formula in T can be decided through true or false by DT. Now, if we want to use the theory in Coq, we must encode it. So there are several possible encodings. If we take T to be arithmetic, we can cite int, z, and nat. Int would be the unary integers, z would be the binary integers, and nat would be the positive unary integers. For dt, we must implement it as well. So for the case of arithmetic, it's the tactic LIA for linear integer arithmetic. And implementation means that there were choices to be made for the representation of the integers. So LIA made the choice to take Z as the standard type to represent integers. So if your goal is expressed with integers in Z, then if it's provable in the theoretical level, then it's provable by the tactic LIA. And if you use other types to represent your data, LIA might not be able to prove it because it doesn't know that these are integers. The solution taken by state-of-the-art tools was to include some goal preprocessing. This is the case of Zedify for the case of LIA. So it's a tactic that takes in input a goal expressed in various types and outputs a goal where integers are all expressed in Z so that LIA is able to prove it. Here's an example of a goal on natural numbers. If you use the raw LIA, it doesn't work, but with Zedify, the goal becomes provable. Here, for knowledgeable people about LIA, I made the distinction between LIA and the preprocessing free version of LIA, which I call LIA star. This is because now in the modern LIA, Zedify is included by default, and I wanted to show the difference between the preprocessing and the automation tactic. So it works with a knowledge base. The user gives associations between types and values, and then it's based on type classes, and the tool will use these type classes to rewrite the goal. So if we take an equivalent goal but expressed in another integer type, so int from the mathcomp library, we can use another layer above Zedify, which is called MCZedify. It's a bunch of declarations for Zedify specific to mathcomp, and thanks to Zedify we can run LIA on this goal and it's provable, which shows that the tool is extensible. Now in the general case, we might want a tool that preprocesses logic as well. We might have tactics that expect the goal to be expressed all in prop or bool. Let's take the example of some SMT tactics that expect the goal to be fully Boolean. Talking about SMT, we would also benefit from a tool able to handle several theories because Zedify focuses on arithmetic, but we would also like to be able to preprocess uninterpreted functions, like in this goal, f is uninterpreted, and if we run an SMT tactic on it, then the goal is proven. Here are two examples of SMT tactics, SMT Coq and iToto. But if we take the exact same goal in int, SMT is not able to prove it, and Zedify is not useful here because it blocks on the symbol f. Which is why we developed Trakt, a generic and extensible proxy. For your information, Trakt means funnel in Norwegian, and we'll see why it's a kind of funnel. First, the user fills a database with commands, which are user-friendly. Then you take your goal G, and thanks to parameters, you will configure the tool to target the automation tactic of your choice, and then the tool will turn G into a G prime thanks to the data in the knowledge base. And the G prime is associated, meaning that the tool also provides a proof that it implies the initial goal, so that if G prime is provable by the automation tactic, we are able to get back a proof of G. Which means the circle tool here is an enhanced version of the automation tactic. And we have an example of this because Trakt has been successfully included into SMT Coq as a preprocessing tool, and it widens the scope of their SMT tactic. Trakt is written in Coq LP, a meta language for Coq based on Lambda Prolog, and we'll come back to it later. Talking about filling the database, here is the command to add an embedding. So you declare the source type T and target type T prime, two functions in both ways, and proves that their compositions are identities. Internally, it's stored as a predicate embedding. When the tactic runs, a query will be made on this predicate to find the information in the database. Here's an example of call to Trakt add embedding with the type int. Now embeddings can also be conditional. For instance, nat is smaller than z, but we can still embed nat into z. We just have to take care about the proofs. One of them is conditional now, it's the capital C here, and we also need to provide a proof that the condition holds for any embedded value. So any value in z coming from nat is positive. Here's the example of call with nat. For symbols, the command is easier. It's just the source symbol S and target symbol S prime, along with a proof that embedding S gives S prime. Internally, it's stored as another predicate called symbol. And here's an example of declaration. Here the F1 is showed with a question mark because according to the types of S and S prime, it might not be needed. Here we are not bound to Coq's type system, so we can have more flexible declarations, and the types of the proofs also depend on the types of the previous parameters, which is quite handy. And it allows us to have symbols with higher arities while still using the same command. So here's an example with a 2 arity symbol. Here you can see that the type of the proof still conveys the idea that we embed S to get S prime, but S takes arguments now. And here's an example. We can add a symbol with the addition, and it works the same way. For relations, we add arity as an argument, and we have to make sure the logic is consistent. So if a relation is in bool and the other is in prop, we need to use an equivalence and add equals true to one of the sides. And if both are in bool, then we can use the equality directly in the proof. Internally, we store this logical information, and here are two instances of calls to Trakt add relation, one for equality, so equality on int and equality on z, and we can also have more complex relations, for example, orderings from MathComp that we can embed into the standard ordering on z values. Now that we have filled the database, we can call the tactic. So Trakt EL, with E being the target embedding type and L the target logical type. Here E is optional, which means that if we don't give it, the tactic will just perform logical preprocessing, which can be useful in some cases. We also have a syntax to add relations on the fly with the with rel syntax. It allows for users to add relations based on locally defined types, like directly in the proof, which adds even more flexibility. And here's the example of call to Trakt before LIA, and the goal was not provable at first, and it becomes provable after running Trakt. So how does the algorithm work? We go under universal quantifiers, then we are going to rewrite the relations into the target relations and introducing embeddings on the arguments. Then we will perform an embedding descent thanks to the lemmas on the symbols. We will also rewrite the zero arity symbols And then we are left with variables that are embedded in every occurrence, which means we can abstract z of in x into an x prime in z and forget the structure. And once we have abstracted all the embedded variables, we can close the quantifiers and have the target goal. Now let's head to the demo. Here's the example file. First we include the target theory, then the source theory, then we can include Trakt, then some proofs here on that. They are not very interesting, it's just what I showed in the slides but done for real. We can add the embedding between nat and z, then 0, then s. Now we're able to pre-process constants on natural numbers. We can do the same with int, so adding the embedding and some symbols, addition, multiplication. Here's another command for another table to manage conversion. Here I add those symbols to the table of conversion, meaning that every time I will find these symbols in the goal, I will be able to use conversion to reduce and make sure I find the add z or mul z which is hidden behind. We can add the relation on orderings and then import an SMT solver. So I chose iToto, but I could have chosen SMT Coq as well. It also works. Now let's take an example of goal, which is close to what I have shown in the slides. Here I can set printing all to make sure you see the various complex relations and projections on structures from MathComp. I'll hide this now. So running Trakt on this goal gives a goal where everything is expressed in Z, and now the SMT solver is able to prove it. Whereas if I don't run Trakt, SMT cannot prove it because it doesn't know all these values are related to integers. I have a few tests for bigger goals. So here with about 30 operations, it still works quite quickly. With a lot of hypotheses, it takes a bit longer, but it's still okay for 30 about. Here I have the same hypothesis, but here you can see I used mul z add z, and now I use the notation with the generic operators. And now for 50 quantifiers, it's not a problem either. Now with the 100 hypotheses here, the tactic will run for a bit longer, about 10 seconds, because it starts to be a bigger goal, and as I use the notations, there's quite an amount of conversion here, but the goal is still provable in the end. Now let's do a recap and talk about the future work. So if we compare the various tools, here Zedify, the layer for MathComp, MCZedify, and Trakt. First, we can see that in the supported theories, they focus on arithmetic for Zedify, as the name suggests. For Trakt, we can use virtually any theory. Actually, no theory is hard-coded in the tool. The symbols handled are theory-specific for Zedify, whereas we also process uninterpreted symbols, which can be very useful. Zedify and MCZedify are extensible thanks to type classes, and for Trakt, it's user-friendly commands, which are a bit better because the user doesn't have to declare something by hand and dive into the internals of the tool. And the tactic is also parameterized to add some data at runtime, I would say. For flexibility, Zedify is designed for LIA. MCZedify is also designed for LIA because it's based on Zedify, but it adds the MathComp source, whereas Trakt is target agnostic, so no target tool is hard-coded either. We can use it with any automation tool. For the symbol detection, Zedify and MCZedify use keyed matching, meaning that for function applications, they compare the heads, and if the heads are the same, then they use full-fledged conversion on the arguments. For Trakt, we use what I call a table-driven conversion. It's very close actually, but we have this table which enables conversion on some symbols, and all the rest is matched syntactically. And the conversion is only called on the head, for example, to reduce the projections. A bit of feedback about metaprogramming with CoqLP. So the first advantage was the HOAS encoding of Coq terms, meaning both quantifiers and abstractions are represented with meta functions. We have no De Bruijn indices. Here's an example of a type checker of Coq terms. To type check the abstraction, you will introduce a locally bound variable called x, and it's a universal constant, meaning we don't have to add it to a var map. Everything is x is bound everywhere and doesn't escape the scope. And we have this prolog arrow in the middle in blue, allowing to assume the type of x without having a var map storing this information. So it's very handy for that kind of applications. And we also have the association between the holes in the Coq terms and the unification variables in Prolog, meaning it's a very high-level meta language. We can leave holes in the terms, and everything is elaborated when giving back the term to Coq. A second advantage is a quote and unquote system. Here's a snippet coming from the code of Trakt. You don't have to understand it, but just for the syntax, the brackets allow quoting a Coq term, and inside this quoted Coq term, we can access the LP syntax. So it works at any depth. We can mix LP and Coq syntax like we want, and we can also use the meta level beta reduction with this specific syntax with the parentheses. Here P is a meta function and X is a Coq term, and we can call the beta reduction at the meta level on this term. We can cite some interesting design questions when building Trakt. So the first question was the declared symbols, how to detect them, where do we add conversion? So like the state of the art, we chose some kind of middle ground between conversion everywhere and conversion nowhere, but it's a difficult question. Second question was the API design. What kinds of symbols do we want to distinguish? So in our case, we distinguish relations, symbols, and embeddings, but some other choices are possible. For the feature amount, this is a very interesting question as well. We want to remain general, but we also want to add a lot of features for the users to pre-process a lot of goals. So it's not easy to maintain a general tool while adding features. The meta language was CoqLP, but there are interesting alternatives that we haven't tested, and maybe they are relevant for that kind of work. For preventing errors, we need to provide some user guidance. So in our commands, we have interesting checks to make sure the database is not filled with bad declarations. But for the tactic, error messages are a hard problem. I will come back to it later. For future work, what we can say is that we have two versions of Trakt being developed. We will make some improvements for Trakt v1, such as bug fixes if some users find bugs and report them. We could add some flexibility in declarations, build better error messages, and add compatibility with the relevant user needs. So our big user is SMTCoq, and so they give us feedback regularly, and it allows to improve the tool. And we also want to develop a second version of Trakt, which will be based on parametricity. The features will roughly be the same, but the second tool will have a a more principled theoretical basis, which is very exciting for the future. So now let's head to the questions and answers. As it was hard to make it interactive, I took the most interesting questions from the reviewers, and I'll try to answer them. Should you have more questions, please head to the Zulip and I will also be happy to answer there. Does the tool preserve readability of the proof state? Well, usually the tool changes x into x prime, f into f prime, etc. But there are some cases where the names are auto-generated and not very nice, but the tool is made to be called with an automation tactic right after, so it's not a big deal. Why does the translation have to be done in two phases when targeting prop? Okay, so this is a quite technical question that comes from the documentation on the website. Okay, so when you target bool, you just have to replace your relation with some Boolean relation and call recursively. And if everything works, you just have to add some equals true somewhere to make sure the typing is correct. In the other way, you need to translate an applied relation with an equal true or false at the end into some prop relation. So this is not exactly the same. There's a kind of look ahead behavior here, which means if we want to unify the code of bool to prop and prop to bool in the same code, well, we have to add a phase for the bool to prop way, which is what we did. However, the improvement we could do is that currently it requires the user to do two declarations, but we could turn it into one. Let's take the example of natiqb, which has to be changed into EQZ. Then we could declare a local definition and then change natiqb into this one and this one into EQZ. And we would add this step internally so that the user only declares natiqb is linked to EQZ, and we can split the proofs and do the work as an internal phase without the user having to do two declarations. How does the plugin behave if a user declaration is missing? In this case, the translation does not happen for the concern symbol, which means we could get an ill-typed term and the tactic could fail. This is the main margin of improvement of Trakt. And adding error messages is hard because we need to make sure the error comes from the user and not a lack of feature. For example, dependent functions are not supported right now. So it's a lot of engineering work actually. It takes time and it's not easy. As I said, it's the main margin of improvement of Trakt. Has the success of Trakt been evaluated empirically? As I said, Trakt has been integrated into SMT-Coq, so it's a kind of nice evaluation that it can be useful in a real-life context. But I have no specific figures to show about performance testing, for example. Do you plan to distribute Trakt along with libraries of pre-filled databases? Actually, that's a great idea. We have thought about it. It would allow the user to not think about standard types and standard proofs to add, especially some specific cases he must not forget for the tool to work correctly. If the first version of Trakt goes a long way, it could be the developers of the libraries that add some declarations for Trakt when the libraries are released, so that the users of the libraries could directly use Trakt with the theories covered by these libraries. But right now we haven't written these libraries because it's a lot of engineering work again, and the second version of Trakt has a lot of research interest as well, so it's hard to find a balance between both. Well, thank you for your attention. You can head to the website if you want to read the documentation, and you can also install Trakt. It's in the standard OPAM repository. And please ask your questions on the Zulip if you want to know more about the tool. And thank you again.